multivariable calculus, autonomous differential equations. And here's a slope field that we're going to look at in a little bit more detail later. Autonomous differential equations, what are they? Well, the definition is a first-order differential equation is autonomous if dy dx equals a function in y. In other words, there are no x terms there on the right. The derivative is completely in terms of y. Notice that since the derivative is in terms of y, the slopes are not affected by x values. So if you are looking at the graph of the slope field, the slopes only vary vertically. The slopes are the same when moving horizontally. So when you're looking at a slope field and you want to know if it represents a first-order differential equation that's autonomous, then just glance sideways from left to right and see if there's any variation in the slope. If there's a variation, it's not autonomous. If they're all exactly the same on each horizontal line that you look at, then it's autonomous. So what about this one? Is this an autonomous, does the slope field represent an autonomous differential equation? Well, what do you think? Yes, because anytime you just move horizontally, you have the same slope, okay? What about this one? What do you think? Anywhere where you just go from west to east, so to speak, or east to west, are the slopes all the same? Yes. What about this one? What do you think? Well, if you look right here, those slopes are positive, but if you go horizontally over to the left, now you've got slopes that are negative. So they're definitely not the same slopes, and therefore the x value must have affected the value of the derivative, and so this is not autonomous. What about this one? No. It varies like a sine curve. You've got negative slopes and positive slopes and negative slopes and positive slopes. On each and every line, you've got variation as you move from left to right. So this one is not autonomous. Okay, now we're going to look at a theorem that has 3 parts. Okay, you ready? Part 1. Given dy dx equals f of y, y equals c is a solution if and only if f of c equals 0. So here we have an autonomous differential equation, and it may have solutions that are just constant functions. And if it does, then that means that f of c has to equal 0. Well, why is that? Well, if y equals c is a specific solution, then its graph is a horizontal line, right? This means that its slope at every point is 0. Hence, y prime's derivative, namely dy dx, has to equal 0, and since dy dx is f of y, and y is always c in this case, then f of c is always going to be 0. Okay? Part 2. Given dy dx equals f of y again, and y1 and y2 are 2 unique solutions, then the graphs of y1 and y2 do not intersect. Now, we're doing all this because it's going to be useful when we look at graphs and solutions in the examples, okay? So why is this true? Why can't 2 solutions intersect? Well, if the graphs of y1 and y2 did intersect, what would their slopes be at the point of intersection? For example, here are 2 graphs that intersect. Now, at the point of intersection, the upside down parabola has a negative slope, and the cubic function has a positive slope. But I mean, they wouldn't have to be so diametrically opposed, but if they intersect, that means they're not parallel. And if they're not parallel, then they have to have different slopes at that point, right? The slopes will be different at the point of intersection. And therefore, since this is an autonomous differential equation, we can't have different slopes at that point of intersection. In fact, no slope field would have a different slope. So autonomous or not, you're not going to have 2 unique solutions ever intersect. But slope fields have unique slopes at every point. Doesn't even have to be autonomous, like I just said. So they can't, these solutions cannot intersect. Okay, now the third part of this theorem is a little bit more convoluted, so let's look at that slowly. Part 3. Given dy dx equals f of y, so we have an autonomous differential equation. Part A, if f of y of 0 is greater than 0, then y is increasing, and furthermore. Well, now remember, f of y is already the derivative. So if it's positive at any value, then we have the original function increasing, and we're picking 0 on the x-axis kind of arbitrarily. Okay, now if f prime of y is greater than 0, then y is concave up, and if f prime of y is negative, then y is concave down. Now that seems obvious, but actually it's a little more complicated than it looks, which we'll explain in just a minute, because part B says that if f of y of 0 is negative, then y is decreasing, and furthermore, if f prime of y is negative, then y is concave up, and if f prime of y is positive, then y is concave down. Well, this is a little bit complicated, so let's take a look at the fact that we have increasing and decreasing based on f of y. We're going to look at that in just a minute. Right now we're going to look at the second derivative, which is, using the chain rule, f prime of y times dy dx, which equals f prime of y times f of y, because f of y is just dy dx. So the concavity is going to depend on f prime of y and f of y. If f prime of y and f of y have the same sign, then y is concave up, and if f prime of y and f of y have different signs, then y is concave down. So in part A, we have a positive f of y, and therefore if f prime is positive, we have a positive second derivative, and if f prime is negative, we have a negative second derivative. But in part B, if y is decreasing, then f is negative. And that means that if f prime is also negative, you get a positive second derivative. And if f prime of y is positive, then you get a negative second derivative. Okay? Now, let's look a little bit more closely at why we're using f of y of 0 to determine increasing and decreasing. Here are two slope fields. The top one is not autonomous, and the bottom one is autonomous. If the graph of y ever changes direction, then some slopes for the same y value will be different, such as in your first example, but that's not autonomous. And so you could have, as you move across, you can have a function that's increasing and decreasing. But the slope fields of autonomous differential equations keep the same slopes for any given y value. And so as you move across, the graph cannot change directions. It's always going to be going down or up. If it changes and goes down for a while and then up for a while, then you're not going to have the same slope as you move horizontally. So if y is a solution for an autonomous differential equation, it is either always increasing or always decreasing. And so we just arbitrarily pick 0 for x and take a look at that slope, and if it's positive, then we know that the graph of y is always increasing, and if it happens to be negative, then it'll be negative always for that y value, and so the graph can't change directions, and so therefore it's always decreasing. Okay? So for instance, look right here. At 0, we know the slope is positive. So if we have a fixed point on the graph of a particular solution at that y value, where x is 0, then we'll know that the entire graph is increasing. Examining the sign of f prime of y at x equals 0 will tell us y's direction. And we could have examined it at x equal 1 or x equal 5 or whatever, but 0 is just a convenient place to check. Okay? Summary. Okay, so here's a slope field that represents an autonomous differential equation, and I don't know if you can see it, but there are 7 specific solutions sketched in. 2 of them are constant solutions, y equals c1 and y equals c2, which means that f, which is the derivative of y, is going to be 0 at those particular values of y. All the other solutions are sort of channeled in between the constant solutions and are unidirectional, because remember, we said that no two graphs in a slope field can intersect, and so if you've got something in between the constant solutions, they can't cross over. And then we also said that because of the no change from left to right, all your solutions will either be increasing or decreasing individually, that is. Example number 1. Find the constant solutions for dy dx equals e to the negative y. Well, part 1 said that given dy dx equals a function of y equals c is a solution if and only if f of c is 0. So e to the negative y would have to equal 0. And remember, f is a function of y. So what y value will make this equation true? Never. So therefore, there are no constant solutions to this autonomous differential equation. Now, just for fun, let's use an old method. Here's our problem. If I separate the variables, I can integrate, and I get e to the y equals x plus c. And then if I take the natural log of both sides, those are all my solutions, which I got very quickly without all this new folderol, just to show you that indeed there are no constant solutions here. There's a picture of our logarithmic solutions, and notice that if we drew a slope field, it would be autonomous. I just showed one line there of parallel slopes. But I digress, so let's move on. Example 2. Find the constant solutions for dy dx equals y squared minus 2y minus 3. Part 1 says again that if we have an autonomous differential equation, dy dx equal a function in y equals c is a solution if and only if f of c is 0. So this time we set y squared minus 2y minus 3 equal to 0, and that will have some solutions because that factors nicely. And therefore our constant solutions are y equal 3 and y equal negative 1. See, that was quick. Example 3. Sketch the graph of the specific solution for dy dx equals the same function as the previous slide, given that y of 0 is 2. Okay? So the constant solutions, you recall from the previous example, were y equal 3 and y equal negative 1. So those sort of bound the Cartesian plane, separate the Cartesian plane into 3 sections where solutions may lie. And in this particular case, y of 0 is 2, so I put a point there. Now, f of y is y squared minus 2y minus 3. F prime of y then is 2y minus 2. And in order to look at our third part of our theorem, we need to look at f of y of 0, which will tell us the direction of this solution. And so you plug 2 in for y into f of y, and you get a negative value. So that means that our function is decreasing. Okay, y is decreasing. So our graph is going to go downhill the entire way. Now we need to look at the second derivative, which is f prime of y times dy dx. In this case, that's 2y minus 2 times dy dx. And so we need to look at when f prime of y is going to change signs, and that's going to be at negative 1. And so my concavity is going to change at y equal 1, and I'm not using an x scale because we're not going to find the x value there, obviously. Okay, so now what's next? Well, dy dx is always negative, and if y is between 1 and 3, which would be the top half of our graph, then 2y minus 2 is going to be positive. And so we have what? Positive times a negative is a negative, and so it's going to be concave down. So we draw that part concave down. Now, what if y is between negative 1 and 1, which is the bottom half of our graph, from the dotted line down to the bottom green line? Well, then 2y minus 2 is going to be negative, and so a negative times a negative is positive, and we have concave up because the second derivative is positive. So the other half of our graph is concave up, and there we have it. Example 4. Sketch the graph of the specific solution for the same autonomous differential equation, but this time given that y of 0 is 4. And again, our constant solutions are the same as before, and there's my point at 0, 4. So our graph is going to be above that top green line. So let's review f of y and f prime of y, and this time we put 4 in for y into f of y, and we get a positive value for f of y, which means y is increasing. Now, the second derivative is y prime of y times dy dx, which is 2y minus 2 dy dx again. But this time, we know that dy dx is positive because y is increasing. And since y is greater than 3, we know that 2y minus 2 is also positive. That gives us a positive value for the second derivative, so we have a graph that's concave up. Increasing, concave up. Looks something like that. Okay, now just because we can, let's look at this the old-fashioned way. Separate the variables, integrate, and we use partial fractions. I didn't show the work, but there's how you change the integrand on the left. And when you integrate it, you get a bunch of logs, and on the right you get x plus k. I then combined the logs by scooting y plus 1 in the denominator. Then I multiplied through by 4. And then I took the anti-log of both sides and dropped the absolute value. I skipped some steps there because a could be positive or negative. And then plugging in 4 for y, I get a equals 1/5. Okay, so now we have y minus 3 over y plus 1 equals 1/5 e to the 4x. And so I didn't show the steps, but if you solve for y, you get this function. Okay, so then I put that into my trusty calculator. Now remember, this is only the specific solution where y equals 4, okay? And so when I graphed it, I actually got a second solution down there at the bottom. But in order to do this, in order to find this solution, our new method would require a second point. So I've digressed again. Sorry about that, but I just get curious. Example 5. Sketch the graph of the specific solution for dy dx equals sine y, given that y of 0 is 11 pi over 6. So different differential equation this time. So we're going to have to look at our constant solutions, which occur whenever sine of y equals 0, which is going to be at y equal any integer times pi. So I just drew a few of them, one on the x-axis, and then at negative pi, pi, 2 pi, and 3 pi, because my point then is going to be up there at 11 pi over 6 for my y value at x equals 0. Okay, so that's a little red dot there. Now, f of y is sine y, f prime of y is cosine y, and f of y of 0 is going to be sine of the y value at 0, which is 11 pi over 6, and that is negative. So that tells me y is decreasing, and it's going to lie in between the constant solutions of y equal 2 pi and y equal pi. The second derivative is f prime of y times dy dx, which is cosine y times dy dx. And so we know that if we have an inflection point, it'll be where cosine y is 0, and that occurs at 3 pi over 2. So there's a dotted line on my graph at 3 pi over 2, and then somewhere, I don't have the x scale, don't need it for the drawing, I have a dot which will be my point of inflection. Now we know that dy dx is always negative because y is decreasing. And if y is between 3 pi over 2 and pi, that would be the lower half of the graph, then cosine y is going to be negative. So we will have concave up. So there's that part of the graph. Now, if y is between 2 pi and 3 pi over 2, that's the top half of the graph, then cosine will be positive and we'll have a negative second derivative, and our graph will be concave down. So it looks something like that. Example 6. Sketch the graph of the specific solution for dy dx equals y e to the y, given that y of 0 is negative 2. Okay, so we're going to have constant solutions whenever y e to the y equals 0, and that's only going to occur for y equals 0. And so there I have that constant solution in green along the x-axis, and a point at 0, -2 for this specific solution that we're working on. So there's f of y, and then using the product rule, there's f prime of y. And then if we plug -2 in for y, we get e to the -2 times -1, and that's going to be negative. Hence, we know that y is decreasing. Now, the second derivative is going to be f prime of y, which I wrote in factored form, times dy dx. And so we are going to have our point of inflection along the line y equal -1, and I've got the dot to the left because y is decreasing. And we know that dy dx is always negative. And if y is between 0 and -1, then we're going to have a positive f prime of y. And so we have a negative second derivative, which means we have concave down. And so it's going to look something like that. They're above the line, between the lines y equals 0 and y equal -1. Furthermore, if y is less than -1, then our f prime of y will be negative, and now we have a positive second derivative. So that bottom half of the graph is going to be concave up. Notice that there is no horizontal asymptote below our curve. So that's just going to continue on down, decreasing concave up without a lower bound. All right, so here is a copy of the worksheet for this section. Again, this section is not in Edwards and Penny, so these problems come from an Ellis Gullick text. Here are the answers to the odd problems. Notice that for the graphs, this particular text only graphs solutions for x greater than or equal to 0. Why they leave off the portion where x is less than 0, I'm not sure. Feel free to fill those in yourself. So here we have a little video of some guy that really likes calculus, and whoever created this obviously had way too much time on their hands, but I thought it was kind of cute. All right, see you next time. Bye-bye.